Morning.
Good morning.
Morning.
All right, it's 8 o'clock, we'll get started. So we were looking at a problem on that was similar to what we had been talking about before with the two half cells and then trying to figure out the voltage and therefore the delta G. In this one, we're looking for the E naught cell, the delta G naught and K. Now I had gotten as far as getting to this part down here where we're dealing with the E naught cell. So just summarizing what we had done. So looking at the cell diagram here, by convention, the Cu and the Cu2 plus are going to be the anode, which means that this is where oxidation occurs. The issue that we face is that every single half reaction that we look at in the standard electrode reduction potentials is indeed a reduction, which means the electrons are on the reactant side of every single equation. In order to turn a reduction into an oxidation, we simply need to flip the reaction, which means the electrons could end up going on the product side. That means they're being given away, and that's what we want. That's what we want to end up seeing. So you can see here that we've got Cu gives Cu2 plus 2 electrons, and that's the flip of the reaction that involves copper. And if I can just find that reaction here. Here we go. Cu2 plus 2 electrons gives copper. This is a reduction. The potential is positive 0.340 volts. I need to turn that into an oxidation. So I flip it around and flip the sign of the E naught as well. So that was positive, now it's negative. Now the importance of this is that we need a reaction that gives away electrons for the first reaction, the one that is mentioned first in the cell diagram. And then the other reaction needs to be a reduction. It needs to take in electrons, and the electrons need to be on the reactant side. So what we're finding is that when we have the two half cells together, one will be giving away electrons and one will be taking them. And that makes a lot of sense because it's the electrons that are being given up by the copper that are being accepted on the other side here of the half cell. Now, the other thing that we'll need to do is to make sure that those electrons are indeed equal. So in this instance, we've got 2 electrons being given away in the top reaction and 4 electrons being accepted in the bottom reaction. So in order to equalize things, what we do is we multiply the top reaction by 2 to make those electrons equal, because the understanding is that the electrons being given in the top reaction need to be accepted in the bottom reaction. And that tells us the number of electrons being transferred as well during the process, which is information we need later. But one of the rules that are associated with these electrode potentials is that when you multiply a reaction, you don't multiply the E naught value. And that's because we talked about this the other day. It's an intrinsic property. meaning it's not affected by how much you have. So multiplying by 2 has no effect on the electrode potential. We do need to do it though, so we can ascertain what this value is with the number of electrons being transferred. So after that, we've got our E naught values, which we add together, that we come out with an E naught cell of 0.109 volts. Using the equation I showed you last time, we have the delta G naught value, which can be found by using NF E naught cell. Now, N is the number of electrons transferred once we've balanced, and that value comes out to be 4. So we have 4 electrons being given by the top reaction, 4 electrons being accepted. So 4 is what we get down here. So it's negative, because we're negative out in the front here. The 96485 joules per volts per mole is a constant value. That's the Faraday constant. And then we've got the E naught cell value, which we calculated from up here as in volts. We want a kilojoules per mole. So we do a conversion here to go from joules to kilojoules. And we end up getting negative 42.1 kilojoules per mole. The other thing we had talked about was the relationship between some of the signs of the different quantities that we could get from these processes. The first thing we can talk about is the fact that if you've got a positive E naught cell, that represents a spontaneous process. So we've got positive 0.109 volts here, and that would indicate that it is indeed a spontaneous process. You'll notice that to get delta G, we have to put a negative out the front of the equation, negative NF E naught cell. If E naught cell is a positive value, then delta G naught will definitely be negative, because N is always positive and F is always positive. So you can see here that this 0.109 volts results in a negative delta G naught, which is what we expect. Again, that indicates a spontaneous process too. Does anybody have any questions about anything so far? Okay, the next thing is the delta G naught is equal to negative RT ln of K. So ln of K can be isolated, and that would give you delta G naught over negative RT, or negative delta G naught over RT. And then we take the inverse natural log of this. We've done this before. We did this way back in, probably the first class that was after test 2. And we can get a K value from that as well. All right, does anybody have any questions at all so far? Now, you won't have a question exactly like this on the test. I'll show you what the test question looks like in a minute. But it will have to do with non-standard cells. Now, the cells that we're looking at here, or this particular cell, is the cell under standard conditions. What does that mean? It means that we're talking about 1 atmosphere, 25 degrees Celsius, and most importantly, 1 molar solutions. So all of these E naughts, all of these reduction potentials are set up for 1 molar solutions. We have an equation that allows us to determine the voltage if the solutions are not 1 molar. So we call these non-standard cells. And for this, we use an equation called the Nernst equation. Not an equation you have to memorize. It's one I give you in the test. And you can see it's E cell. Now, you'll notice there's no naught on the E cell here. There's no naught here because it's not standard. And what makes it not standard is the fact that these molarities for the solution parts of the cell are not 1 molar, as you can see here. At least not all 1 molar. You've got 0.5, we have 1 here, we have 0.5, and we have 2. So we have molarities that aren't standard here. Now, if you look at the Nernst equation itself, it's actually not as complicated as perhaps it might look. It's based upon E naught cell. So you do need to find E naught cell first, which means you need to find what the voltage is under standard conditions. And then the rest of this is what I would call like a modifier. It's kind of like a correcting factor, if you will, that allows you to say, well, what's the difference between the E naught cell value and the E cell value, and that would be whatever is over here. This 0.0592 volts is a mixture of constants that includes the temperature at 298 K and the Faraday constant and some other things involved there as well. But all of those things are multiplied out and divided to give you this 0.0592 volts as a constant value. The N here again represents the number of electrons transferred in the balanced process. And the log Q, the Q here is our friend reaction quotient, which we talked about way back in test 1. It's the products over the reactants, but we're only talking about anything that has a concentration associated with it. And if you remember what Q is, it's like K, except it can be done at any condition, including equilibrium, but also other conditions that are not equilibrium conditions as well. So here's an example of how we can apply the E cell value of the Nernst equation. And it's very similar to what we had just done, except now you're dealing with situations where the aqueous solutions are actually quoted as having certain concentrations, and you can see they're in parentheses beside each one. You'll notice that the solids, like the copper solid here, well, I guess that's it. The copper solid doesn't have a concentration associated with it because it's a solid. So anything that's solid will not have a concentration, won't be listed. Everything else will have a concentration in molarity here. As I had talked about last time, the platinum here is going to be necessary in situations where there's nothing solid metal to act as an electrode to actually be able to transfer electrons. So we need a platinum wire in there. We ignore the platinum when we're looking for the reactions that are associated with this kind of setup. All right, so let's have a look at how we proceed with this process. The first thing we need to do is find E0 cell, so the cell potential under standard conditions, which means we again look for a reaction that involves copper and copper 2+. And you can see we've got copper 2+ and copper. Remember, the order up here doesn't really matter because we're just going to go ahead and find a reaction that matches that. So we come out with copper 2+ plus 2 electrons gives copper, positive 0.340 volts. Now this is a reduction. As I had stated earlier, anything that's listed first is the anode, which means that's where oxidation occurs. So the first thing you should do is flip it. And the copper then goes to copper 2+ and 2 electrons, and the E0 then gets flipped in sign to be negative 0.340 volts. I'm going to stop here for a second. Does anybody have any questions about why I'm taking, well, how, first of all, I'm getting that reaction and then why I'm flipping it? Is everybody okay with that? Okay. The next thing I need to do is I need to find a reaction that involves Mn2+, MnO4- and H3O+. Now, realizing that H3O+ equates to H+, both of those are the same thing. H+ is always going to be in water and will always be associated with water and will always form H3O+ anyway. But I just want you to realize that if you see H3O+, you're really looking for H+. So let's go take a look for something that involves all of those species. So I'm looking up here. I see I've got MnO4- here. I've got H+. That's cool so far. But over here, I've got MnO2 solid. That's not Mn2+. So I have to be a little bit careful. I have to make sure that any reaction I pick does indeed contain everything that's listed on that side of the cell equation. So what I am, again, what I'm looking for, Mn2+, MnO4- and H3O+. So I have to keep on hunting here and see if I can find it. Now here's one here, MnO4-, H+, Mn2+. There we go. That's the one we want. So I take that And I don't have to balance it or anything. It is what it is. It's already balanced. So I could just take that directly and put it in as my second equation. This is already a reduction, so it stays that way. And that's what's been done over here. So I've left the reaction the way it is and quoted what the E naught value was that was in the table. And you can see that's 1.51 volts. There it is up there. Does anybody have any questions so far? Now remember, these are electron transfer processes, so the electrons need to be equal. Now presently, there are 2 electrons being given by the top reaction and 5 electrons being received by the bottom reaction. So what I need to do is find a way to make those electrons equal. So what I do is I multiply the top one by 5 and the bottom one by 2. This allows me to have 10 electrons being transferred from the top reaction to the bottom reaction. The method of doing this is very similar to what we do when we add fractions, when we look for a lowest common denominator. So we're looking kind of for a lowest common factor here between 5 and 2, and it turns out that it's 10. Does anybody have any questions about why we're multiplying by 5 and 2 here? You'll notice again that when we multiply by these numbers, it has no effect on the E naught values. Right, that's one of the rules. Just because we multiply a reaction doesn't mean we multiply the E naught. So after that, you can see that we add those reactions together. We add the E naughts together to get the E naught cell. That's 1.17 volts positive. But you'll also notice that these figures get pulled down here as well. We're going to have 5 copper solid. We'll also have 2 MnO4 minus and then 16H plus. Now the 16H plus comes from 2 times 8 over here. So we're multiplying everything that's in these parentheses here. On the product side, we've got 5 copper 2 plus. The electrons cancel because we had 10 electrons on the top and 10 electrons on the bottom. We multiply everything here by 2, so it's 2 Mn2 plus and then 8 waters down here in the final part of the equation. Does anybody have any questions about what I did there as far as adding the reactions together? The next step then is to calculate Q, because we do have our equation, the Nernst equation, which is 0.0592 volts over N. We've got N now. N is 10. That's the number of electrons transferred once we balanced it. That's 10. Log of Q is what we need now. So, and that's log to base 10 of Q, by the way, not natural log, because it's log. The Q is going to be anything that has a concentration associated with it, and it's always products divided by reactants. So we've got Cu2 plus, now that's to the power of 5, and Mn2 plus, that's to the power of 2. On the bottom, we've got MnO4 minus, that's to the power of 2, and H plus, that's to the power of 16. You'll notice that in the Q expression itself, there's no mention of any solids, and there's no mention of water. Just anything that has a concentration associated with it. A good double check is to move back up to the original equation that you've been given, up to the original cell diagram. And just make sure that everything in the cell diagram that has a concentration next to it is also in your Q expression. Because those are the only things that will be in the Q expression, other things that actually have concentrations. So that's a good double check for you to do, to make sure you've included everything you need to include in the Q expression. Does anybody have anything that they want to ask about at this point? So after that, what we do is we plug in all of those concentrations that are in the question. So we've got 0.50 for copper 2 plus, we've got 1.00 for Mn2 plus, we've got 2.00 for H plus, and we've got 0.50 for MnO4 minus. So all of that just gets plugged in, along with the powers, of course, that are in the Q expression. And that allows us to spit out a number. In this case, it's 1.9 times 10 to the negative 6. So after we do the math on that, we've got our 1.17 volts, which is the E0 cell. So that's the standard cell voltage. And then that's minus 0.0592 volts, again, a constant, divided by 10. The 10 is the number of electrons transferred in the balanced set of equations. 5 times 2 is 10, 2 times 5 is 10, whatever it takes to make those electrons cancel out when we add the reactions together. And then we put in the log of log of the base 10 of the Q value we just calculated. And you can see here we end up with a value of 1.20 volts. So generally speaking, what you're going to find is that the E cell values themselves are not going to be overly far out from the E0 cell value you start with. So you'll notice we have 1.17 volts as the E0 cell value, and our answer here came out to be 1.20 volts, and that's only 0.03 volts different. So just a small difference here. But the difference is due to the fact that we're using not 1 molar solutions all the way through. All right, does anybody have any questions about any of that? Because that's what you're going to have to do on the test. You're going to have to come up with a voltage for a non-standard cell. Anybody have any questions at all? Okay, we can do the same thing if there's any pressures as well. As long as those pressures are in atmospheres, then we treat them just like concentrations. So if we've got gases, and you can see we've got NO gas in this particular cell, as long as we're quoted a partial pressure for that gas, in this case we are, it's 2.00 atmospheres, we treat it just like we would a regular concentration once we do the Q value. So you can see that in the Q value down here, we've got Cu2 plus cubed, and then we've got PNO squared. So that's just the partial pressure that's quoted here. So it just gets plugged straight in, just like a concentration would. So that's just a little wrinkle that can occur in these reactions when you're given a gas, but it doesn't really affect anything. And you'll notice again, the E0 cell voltage here was 0.616 volts, and over here it was 0.637 volts as the final voltage. Not overly different from what we had started with. All right, so I just wanted to mention that example just to tell you what you would do if you ever saw any pressures instead of concentrations in amongst your values. But the method here is exactly the same as what I've just gone through. Does anybody have any questions? All right, let's go take a look. I just wanted to alert you to something here. Next Tuesday, next Tuesday is Discovery Day. There is no class on Tuesday. Okay, it's a faculty development day, so there is no class for anybody for any. There's no classes on Tuesday at all for anything. So just be aware of that. I think some people might turn up on Tuesday thinking there's a class, but there isn't. Yeah, it's next week. All right, let's take a look. Let's take a look at the test here, and I'll show you what the test question looks like. It doesn't look overly different to what we had just talked about. All right, so it's under non-standard cells in the Nernst equation. You'll notice that I actually do give you the reduction potential reaction for any of the possible, cathodes here. Yeah, so there's only going to be two possible cathodes. It's like either going to be MnO4 minus goes to MnO2 or MnO4 minus goes to Mn2 plus. They're both listed here, so you don't have to go hunt those down. You don't have to have the table in front of you because I give you those values. Now, the other thing I give you is the reduction potential for X4 plus. Now, what does that mean? If I'm giving you a reduction potential for X4 plus, this is often confusing to people. What I'm saying is this: X4 plus 4 electrons gives X solid. Now that's the actual reduction reaction there, and the potential there, the E naught, is 1.7 volts. Now how do I come up with that? Well, I come up with that because in order to make the 4 plus 0 effectively, I have to add 4 electrons to it. And it has to be expressed as a reduction, which means the electrons have to be on the reactant side. So reduction is always pretty much what it says. It's like a reduction in charge. So the 4 plus is effectively going to 0. That's what makes it a reduction. But that's where I come up with that. So that would be the first reaction. And that ends up being flipped. So then it becomes X gives X4 plus 4 electrons. And then we've got our other reaction. We just have to pick out of those two that are given. We've got, it looks like it's MnO4 minus, Mn2 plus, and H plus. Okay, let me shrink this a little bit, see if I can. So I pick out the one that matches what I've got down here, and it would be, let's see, MnO4 minus plus 8H plus plus 5 electrons. And that gives Mn2 plus 4H2O. So you can assume that that's already balanced. Now we've got our voltages here. This one would be negative 1.57 volts. Now remember, it's negative because we had to flip it around. Because what was quoted was the reduction potential, but the first step is always turning it into an oxidation. So that's why that's negative now. And the MnO4 minus, that keeps its voltage at 1.51 volts. Does anybody have any questions so far? Now I know that in order to make these electrons equal, I'm going to have to multiply the top one by 5 and the bottom one by 4. Now, that's not very, it's not very clear, is it? Let's, okay, here we go. So I have to do 5 times the top reaction and 4 times the bottom reaction here. Does anybody have any questions about why I'm doing that? So over here on the left side, I've got 5x, and I'll have 4 MnO4 minus, and I'll have 32H plus. And on the other side, I'll have 5X4 plus and 4 Mn2 plus and 16H2O. Then I add the voltages together here, and I get, let's see, negative 1.51. That's it must be negative 0.06 volts, which actually turns out to be a non-spontaneous process in its standard form. It's possible, though, that in non-standard form, it might actually be spontaneous. This negative could turn into a positive as long as the equation works out. You'll notice I do quote the equation down here as well. Does anybody have any questions so far about what I'm doing? So this represents, again, the E0 cell value, this negative 0.06 volts, which is the sum of the 2 voltages that we have up here for the reactions, which again didn't get multiplied, by the way. So we've got E cell is equal to E0 cell, which we have already, minus 0.0592 divided by N times the log to base 10 of Q. So we still need to find, now we do have N. N is, oops, N is not 10. N is 20. N is 20. And how do I get that? It's 5 times 4 is 20. 4 times 5 is 20. So it's whatever we had to make the electrons so that they evened out. So N is 20. The Q value here is going to be based on what you see in the equation. And it's going to be, let's see, Mn2 plus, products over reactants, Mn2 plus to the power of 4. And it'll be X4 plus to the power of 5 over MnO4 minus to the 4th and H plus to the power of 32. And then we can substitute in our values here. We've got Mn2 plus, that's 2.58. And that's to the 4th. And then we've got, let's see, X4 plus, that's 1.38. And that's to the power of 5. And then you've got MnO4 minus, that's 0.44. And that's to the power of 4. And then you've got H plus, which is 1.09, and that's to the power of 32. All right, I'm going to stop here for a second. Does anybody have any questions about where I'm getting any of this stuff from? Anybody have any questions? All right, so I put that in my calculator. Now remember, you'll be using the Honorlock calculator, so you'll have to practice with doing this on the analog calculator. You've got 1.38. And I end up getting 375 for that value. So the Q here is going to be 375. And then we can go ahead and calculate our E cell, which is going to be, let's see, negative 0.06 volts. And that's going to be minus 0.0592 divided by 20 times the log of 375. And for that, it doesn't change it much. It becomes negative 0.07. So that's going to be my answer there. So that wouldn't be a spontaneous process either. Does anybody have any questions about any of this? Now remember, if you're uncertain about how to do any of these test problems, you can always look at the video that's specific for this problem on the test. So what question is it? Question 8. Yeah, so you'll be able to, well, not question 8, question 7. Yeah, so you look at question 7 and it will tell you how to handle that. Does anybody have any questions at all? Anything at all? All right. So it'll be practice, 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 practice. All right, let me see how far we had to get today. I have a suspicion. Let's have a look. Just want to see if I'm going to cover electrochemical stoichiometry today or not. No, not today. All right. Let me show you, let me show you, let's go back to the fun quizzes here. Okay. So this is the fun quiz. And you'll see it's kind of similar to what you're doing on the test as well. So you'll notice again, you've been given the reduction potential for X2 plus, so you have to come up with the equation for that. And then you've given the anode here as well. Now you're going to have to look that up, but you'll look it up on the tables here in order to get that. So that's in the fun quiz. In the real test, you're actually given those values. You don't have to hunt for them. So that's the main difference. And again, you'll come up with an answer for that as well. So that's good practice too for you to do. But again, same deal. So if anybody says they're confused, I'm just going to point them to the recording for this lecture we just did. Does anybody have anything that they want to talk about here? Anything at all? Well, that's pretty much all I had wanted to cover today anyway. So I guess that's it. So I will be in lab, but I'll only be answering any questions anybody has about the lab we were doing, which I went over last week. But if anybody's got anything specific, I'll be hanging around a little bit for lab, which will be at 9:30. All right, but for everybody else, this is it. So why don't you spend some time now practicing some of the problems we just went over and see how you go. If you have any questions, you can always call or email me. All right, so that's it, folks.
Good. Thank you.
I'll see you later.
Good day, Professor. See you on Thursday.
Yeah, see you Thursday.
Thank you. Have a good one.
You too.
Hi, thank you.
No worries. Jack, can I do something for you?